Welcome to Pharmaceutical Calculations, a conceptual approach, lesson 2, errors associated with measurements. If you haven't attended lesson 1, please do so, as many of the important concepts were extensively discussed in lesson 1 and are not going to be repeated here. Our objectives for today is to further refine the definition we have given of the sensitivity requirement of a balance in lesson 1, then demonstrate how to calculate the error and percent error associated with a measurement, and finally learn how to calculate the least allowable weight of a drug at a maximum allowable error. Now, the two most common mechanical prescription balances are class A and class 3, and they usually have a weighing capacity of 60 to 120 milligrams and an SR of 5 to 10 milligrams. For our purpose here, I routinely use 6 milligrams, just easier for you to remember. Now beneath I have placed a schematic of a readout of a mechanical balance. The weights always go on the right pan, and samples to be measured always go on the left pan. Now before start using these kind of balances, you need to make sure that they are leveled horizontally on the bench. Make sure also that the pans are clean to avoid any contamination, and it is a good habit to place weights and samples on the center of each pan. That's a very good habit. As I mentioned before, weights go on the right pan, samples go on the left pan. Balances measure weights by balancing. Place weights on the right pan. Place your sample on the left pan, unlock your balance, and turn the readout knob until the two arms at level are exactly the same height. Let us now refine the definition of SR as we previously defined it in lesson 1. Strictly speaking, SR is defined as the smallest weight required to cause a shift of the balance marker by one division from the zero position. This is a zero position. A shift of one division left or right, that's why plus or minus, for example, 6. So what would the measured value of a known mass, for example 100 milligrams, be read on a balance of SR equal to 6 milligrams? As we extensively discussed in lesson 1, you would expect to measure a value of between 94 to 106. So usually the maximum potential error in the measurement should span about twice the size of the SR, 12 milligrams in this case. Let us now describe the formulas. Excuse me. Equation 1.1 is used to calculate the error associated with a measurement as the difference of the actual value minus the desired value. Equation 1.2 is similar, it's actually identical to equation 1.1, but it is used to determine the SR of a balance, as long as you make sure that the weights you are using are small enough to deflect the readout pointer by one division from the rest point, from the zero position. Equation 1.4 and 1.5 is used to determine the percent error associated with a measurement from the measure and the desired value. Now, anytime you wish to determine the least allowable weight, you have to set the desired value equal to the least allowable weight and solve equation 1.4 for the desired value. And we're going to see how to do that in a few minutes. A word of caution here. Depending on how a question is phrased, it is not always easy to distinguish the desired from the actual value. Let us take a look of this particular problem before we forget in example 1.2. So in this example, you weighted on a class A prescription balance 600 milligrams of HCTZ. When checked on a high precision analytical balance, the true weight was found to be 570 milligrams. calculate the error and percent error. So first we write the equation for the error, which is equation 1, and that's the actual value minus the desired value. The question here is which one is which? Which one is the desired value and which one is the actual value? Well, the first sentence, it says you weighted on a class A prescription balance 600 milligrams of HCTZ. Essentially, this is the wishful thinking, right? It was desired to measure 600 milligrams of HCTZ. You don't know how much you actually measure at this point, right? So that's the desired value. This is what you wanted to measure. However, when you took that measurement on a high precision analytical balance, it was found that that was actually 570. So the 570 milligrams is the actual value and the 600 milligrams is the desired value. This phrasing over here, the true weight, is misleading. The true weight is the actual value in this case. So plugging in the numbers now, 570 milligrams minus 6. So essentially the drug dose is 30 milligrams less than the desired one. We can use formulas 1, 1, 2, and 5 to calculate several of the parameters written in those equations. First, as we have just seen in example 1, in the previous example, we can calculate the error associated with a measurement from the actual and the desired value, the difference of it, right? We can also determine the SR of the balance using the same equation. We just have to make sure though that the weights we're using to determine the SR are small enough to deflect the readout pointer by 1 division in the scale markings, okay? We can also use equation 1.4 or 1.5 to determine the percent error associated with the measurement, as long as we know the actual and desired value. Now, we could use the same equations, 1.4 or 1.5, to determine the least allowable weight. In this case, you need to set the desired value equal to least allowable weight and then solve the equation for the least allowable weight. So this is the equation you use when you reorganize equation 1.4 or 1.5. Okay? So the least allowable weight is equal to SR over percent error times 100. Finally, you can calculate the actual value using equation 1.1. Here is the equation. If you know the error and the desired value, or you can determine the actual value from equation 1.4 if you know the percent error and the desired value. Now notice that error and percent error are related, but they are very different quantities. In fact, error is best known as the absolute error and it carries units. On the other hand, percent error is a ratio, is known as the relative error, and is unitless. Let us solve one example to make sure that we do understand the difference between these two parameters. Here, example MS1, MS-1. Calculate the actual value of the drug HCTZ measured on a balance. If the error is minus 30 milligrams, you see that this is the absolute error, it has units. And the percent error associated with the measurement is minus 5. Now, the measurement, the desired value, is 600 milligrams. So we can calculate the actual value using equation 1.1 or 1.4. Let us take a look. If you use equation 1.1, the actual value is equal to the error plus the true value, right? Reorganizing equation 1.1. This is the desired, same thing as the desired value, right? So the error is minus 30 milligrams. The desired value is 600 milligrams, and therefore the actual value measured was 570 milligrams. If you use equation 1.4, you need to reorganize the equation with respect to the actual value. So when you reorganize it, you get this equation here. And now the percent error is 5. Negative 5, remember the sign. The desired value is 600, and when you apply the numbers there, you get the same answer, of course. So notice, error is the absolute error, has units, percent error is a ratio, is the relative error, and it's just a number. And of course, it can always be plus or minus. Let us now take a look or go through a more involved example. Example 101, you wish to dissolve 6 grams of drug X in 100 ml of water. So this is you wish, right? So this is the desired volume, V desired. And of course, the 6 grams over 100 ml is the desired concentration. You measured 100 ml of water in a graduated cylinder, but the actual amount of water transfer was only 98 ml because of a parallax error. So this is really the V, the actual measurement. You need to calculate the error and percent error in the measurement. Be very cautious with that, in the measurement. B, you need to calculate the desired drug concentration. And you also need to calculate the actual drug concentration. C, what is the percent error in drug concentration? Notice the difference between these two. One is asking you the percent error in the measurement, the other one is asking you the percent error in drug concentration. And the final question, how many milligrams of drug are in half a teaspoonful? That's the dose. Okay, let's start with question A. To calculate the error in the measurement, that's what it's asking, right? Subtract the actual value minus the desired value, so 98 ml minus 100 ml, that's negative 2 ml. That's the absolute error, has units. To calculate the percent error, use equation 1-4. I'm using the error there, so that's minus 2 over 100 ml, that's the desired value, right? So the percent error associated with the measurement is negative 2, no units. B, the desired concentration is of course 6 grams over 100 ml, whereas the actual concentration is 6 grams over 98 ml. So if you increase that, or if you reduce this quantity, if you normalize this quantity per 100 ml, so 6 grams in 98 ml, in 1000 ml, how much? This X will be equal to 6.12 grams. Next, calculate the percent error associated with the drug concentration. So that would be C actual minus C desired over C desired. So that's 6.12 minus 6 over 6 times 100, and that's 2. Notice that the percent error associated with the measurement was negative 2, whereas the percent error associated with the concentration is positive 2. The reason for that is because we have added less volume. We have added 98 ml instead of 100 ml, and therefore the drug concentration is more concentrated. Okay, that's why the positive error there. Now, to calculate the amount of drug present in half a teaspoonful, 1 teaspoonful is basically 5 ml. Therefore, we have half a teaspoonful of 2.5 ml. Set up your ratio, 98 ml, we have 6 grams, 2.5 ml, how much? And X is equal to 153 milligrams. If you have measured the drug quantity, the volume, exactly to 100, the dose would be 150 milligrams. So you are overdosing your patient by 3 milligrams. I would say 2% error in this case is acceptable. Now please try to work out the exercises that are included here. I have also added the answers just to make sure you know where to stop. And at this point, I would like to thank you for your attention. Until next time.